let's do an example of finding the singular values of a matrix. So this isn't too complicated. So essentially the matrix we're considering is the matrix which I'll call A with entries 1, 1, 0, 2. Okay, now how do we find the singular values of a matrix? I think before we actually delve into the problem, it's kind of important to outline the steps. So the first step we want to take is we want to construct the matrix AH, where A denotes the conjugate transpose. In our case, this is just a real matrix. Like the entries are real values, and so this is just equal to the transpose. So let me write that. Or we find A times A transpose. Yeah, so in our case here, since our matrix is 2 by 2, it doesn't make that big a difference which one we choose, but in following examples, which I will do, depending on the size of our matrix, the resulting matrix A transpose A or A transpose will have different sizes. So these two matrices will be of different sizes, and so the smaller size generally would be it would be an easier matrix with which we could do our computation. So this is the first step. We want to find this. The second step is we want to find the eigenvectors, or sorry, the eigenvalues of ATA, or again of A transpose. How do we do that? Well, we just compute the determinant of A transpose A minus lambda times the identity. And we set that is equal to 0. So that's not too complicated. And then the third and final part, to find the singular values, is for every lambda, say lambda I bigger than 0, we define our singular value, so sigma, is equal to the square root of lambda I. Okay, so why don't we do that? Let's start with the first step here. The first step, we want to find, well, let's do A transpose A. Okay, so the transpose here is 1, 0, 1, 2. And this multiplies our matrix A, 1, 1, 0, 2. And so doing matrix multiplication, we go row by column. So our first entry here is 1. This row times the second column gives us 1 again. This gives us 1, and this gives us 5. So we have our matrix here. That's our first step. Now we want to find the eigenvalues of this matrix. Let me move this up here. Actually, let me keep it here so that we see what our second step is. So we want to find the eigenvalues. How do we do that? We compute the determinant of A transpose A minus lambda times the identity. Okay. So this is this matrix, and we take out lambda on the principal diagonal, so 5 minus lambda over here. Boom. Oh, sorry, wrong notation here. Since we're computing the determinant, we'll write it like this. Okay, we have this now. How do we compute the determinant of a 2 by 2 matrix? So let's recall, we basically multiply the diagonals here, so we go 1 minus lambda times 5 minus lambda, and we do minus 1 times 1, so just 1. Let's expand that. So expanding that, we get 5 plus lambda squared minus 6 lambda, and then this minus 1 over here. And so we can rewrite this like this, plus lambda minus 6 lambda minus 1, minus 4. Okay, so we have that. Unfortunately, we can't really factorize this, so we have to use our good old friend, the quadratic formula. So we get for values, our lambda values 1 and 2, we get 6 plus minus, this would be 36 minus 4 times 4. And then we have to divide by 2. Since the coefficient here is 1, so that multiplies 2a. But a is equal to 1, so that's just 2. We can simplify this. This is just arithmetic, so I'm not really going to delve too deeply into this, but we essentially end up with this, plus minus 5, after doing some arithmetic. Okay, let's go back. Our third step here, where we've done our second step, check. Our third step here is to find our sigma values over here. So how do we do that? Basically, we take the square root of this. So our lambda values here would essentially mean that our sigma values are equal to this. So this is 3 plus minus 5. And do note that our lambda values, our eigenvalues, are non-zero, and in fact they're both positive. So we take all the non-zero values and we take their square root, and so this is what we obtain. Boom.